All right, so hello all and welcome to the final University of Alberta Geotechnical Graduate Student Seminar of the 2020-2021 school year. We'll be on hiatus until the fall semester kicks off in September of this year. I'd also quickly just like to thank the team that was involved in making these presentations a success this year. This includes Fernanda Imamura, who has been running the Zoom platform for all the presentations, MEng Liao, who has been preparing the weekly promotional posters, Lang Yu, who is our Q&A moderator, Nabil Islam, who helps with attendance in the Zoom platform as well, our leader and the backbone of the geotechnical department, Vivian Zhang, and of course, all the presenters who took the time to prepare all the great presentations that we received this year. So thank you all for your great work. Today we'll have a presentation from Leanne McLaren, who is between two worlds at the moment as she is working on completing her Master's of Engineering while simultaneously working for Thurber Engineering in Edmonton. Leanne's technical interests include slope stability remediation, instrumentation and foundation design. Outside of work, Leanne is passionate about promoting women and young professionals in engineering and has been a very active participant with the Canadian Geotechnical Society as a member of the GeoVirtual and GeoCalgary Conference Organization committees and acted as the Southern Regional Director from September 2017 to December 2020. Leanne's presentation today is focused on using instrumentation data to assess the performance of a tied-back secant pile wall in Peace River, Alberta. The Peace River region in Northern Alberta is well known for slope failures affecting both rail and highways within the river valley system. A secant pile wall was constructed near the town of Peace River subsequent to slope movements noted in 2015. This wall was divided into 6 sections with varying combinations of cast-in-place concrete piles and soil anchors. Leanne's work focuses on one of the sections of this wall to study its performance, comparing the initial design to the gathered instrumentation data. Please join me in welcoming Leanne.
Thank you so much for that introduction, Kevin. Good afternoon, and thank you so much, everybody, for attending this talk. I'm excited to share my project with you today, as Kevin said, using instrumentation data to assess the performance of a tied-back secant pile wall in Peace River, Alberta. I have definitely noticed that these paper titles in universities just roll off the tongue so beautifully. Before I get started, I just wanted to thank Thurber Engineering for allowing me to use the instrument and construction data for my project, and to Alberta Transportation for allowing me to share this very interesting project with you all today. So I'm just going to start up with a little bit of background on the project and a brief overview of the design. The project site is just, east outside of the town of Peace River along Highway 2, as you can see by the orange arrow in the Google Maps right there. As you can see by the yellow outline on the LiDAR image on the right, this area is part of an ancient landslide terrain that extends from the slope just above the highway down to the North Heart River below. This ancient landslide includes multiple slumps and slope movements, including the one in this study, which is on the west side of the yellow outline. It's in this little green part right here. The highway was built through this area in 1956, but the slope movement caused the highway to drop by several meters. So the highway was realigned to try to avoid the landslide terrain. You can see the green line here is where the highway used to be, and then they rerouted it to try to get above the landslide terrain. The slope movement continued, and in 1998, a cast-in-place cantilever pile wall was constructed downslope of the highway, which can be seen on the red line in the LiDAR drawing. So these photos were taken in 2016 of the existing cantilever pile wall. In the photo on the right, you can see the slope inclinometers both upslope and downslope of the wall. And you can also see that the soils in front of the wall have been creeping downwards little by little. Fortunately, or unfortunately, because of the active movement of this slope, there's plenty of instrumentation data dating at least to the 90s. In this zoomed in site plan, you can see the orange line is the existing cantilever wall, and some instrumentation was installed west of the wall in 2010 here. You can see in the slope inclinometer plot on the right, which shows cumulative deflection on the left and incremental deflection on the right, that there's a distinct slip plane at about 6 meters depth in SI 10-4, which is highlighted in yellow here on the left. So you can see that jumping out right there. Many of the SIs installed between the 1990s up to 2014 showed slip planes between 6 meters and 18 meters depth. And some were sheared off at these depths with maximum deflection rates as high as 87 millimeters per year before they were sheared off. Here's a couple of other SI plots prior to construction. The one on the left is SI 13-2, which was just upslope of what would become the new wall. And the one on the right is downslope into the west of the section of wall that I'm looking at. Both plots, again, show a potential slip plane at around 17 or 18 meters depth. With instrumented evidence of continued slope movement and cracks and dips being noted in the highway during the annual geohazard inspections, it was decided in 2015 to build a wall to protect the highway from the slope movement. The picture on the right is a little bit dark, but you can see in both of these pictures, there's several longitudinal cracks running along the highway, and these are caused by loss of embankment support on the downslope side of the highway. So if this wasn't constructed, then the highway would continue to be affected by the slope movement. So 3 geotechnical investigations were carried out between 2010 and 2014 to determine soil conditions and possible causes of the slope movement. Generally, the stratigraphy followed the log that I have here, starting with embankment clay fill on the top, over medium to high plastic lacustrine clay, over varying thicknesses of silty sand, which was on top of very stiff glacial clay till. Several holes encountered colluvium at the surface, which makes sense considering the active slide terrain. And as with many of the landslides in the Peace River Valley, the slip surface was found to be between the high plastic or medium to high plastic lacustrine clay and the very stiff clay till layers. The water table was generally 9 to 10 meters above the assumed slip surface. So water pressure on the slip surface could also speed up weathering, as well as the loss of cohesion in the clay materials, and could provide lubrication along the slip surface once it was formed. During the preliminary engineering phase, SlopeW, the limit equilibrium software, was used to estimate the lateral resistance required in the wall anchor system to increase the slope to an acceptable factor of safety. This lateral resistance was then converted to an equivalent lateral earth pressure with a triangular distribution as shown here to the left of the wall, acting above the slip surface on the back of the wall. This earth pressure load would be resisted by the passive earth pressure in front of the piles and below the slip surface, based on an ultimate resistance of 1600 kPa in the high plastic lacustrine clay and 2500 kPa in the clay till. The piles and anchors themselves were designed by another structural engineering firm, so I wasn't privy to all of the details or parameters used in design except for these values shown here. So now I'll tell you why I keep saying section 4. The wall was designed in 6 sections in total with varying designs based on depth to slip plane. There were so many different aspects that went into the design of each section, so I focused my project on section 4, which had the deepest slip surface, the most robust pile design, and the most levels of anchors. So it's between these blue lines here, as you can see on the plan view. This section was designed with 23 1.5 meter diameter piles. The piles were reinforced concrete cast in place piles supported in behind by 24 0.9 meter concrete piles just to support the front row. The cross section here shows that the section was designed with a 2.2 meter high whaler or pile cap and 30 meter deep piles coming down here. And as you can see, there are 5 rows of anchors, 2 through the whaler and 3 through the pile. The anchors were 32 millimeters diameter high strength threaded steel stressing bars with a 12 meter long bond zone and varying free stress zones so that the bond zone was beneath the slip surface. Service loads were designed to limit deflection of the pile head to 50 millimeters or less. Some deflection was anticipated during construction as the soils in front of the wall were excavated and the anchors were locked off. The soil in front of the wall was excavated in benches so that each row of anchors could be installed and locked off prior to excavating to the next bench. After all 5 rows were installed and locked off, the soil was backfilled to cover the lowest row of anchors. You can see in the photo on the left, the soil's been excavated to get down to the 5th level of anchors. And to the right, they've backfilled it to cover that 5th row of anchors, and that would be the final grade. You can also see in the middle, the instrument monitoring station here. All of the instruments installed within the piles and the pile wall were wired into this data logger, which is powered by a battery and solar panel, so that taking readings at the biannual geohazard inspections would be a simple download from this station. Between 1996 and 2015, 29 different instruments were read annually to assess the condition of the slope movement at this site. This includes 12 slope inclinometers, 3 of which were sheared off shortly after installation, 15 pneumatic piezometers to measure groundwater levels, and 2 standpipe piezometers. There were more SIs installed prior to 2010 in this area, but they had been sheared off or damaged. During construction, several instruments were installed in pile P74, which is roughly in the center of the wall section 4. 28 vibrating wire strain gauges were installed as shown in the photo. So we've got 14 gauges here on the upslope side of the cage and 14 gauges on the downslope side of the cage. And the PVC conduit here is where the SAA or the Shape Accel Array will be installed after casting of the pile. The strain gauges would measure microstrains along the pile between 0.2 and 28.2 meters length. The SAA would measure deflections in the pile similar to a slope inclinometer, and a vibrating wire load cell was installed on each anchor to measure the loads on each anchor during and after construction. All of the instruments were read during construction as part of the observational approach to determine whether or not the pile and anchor designs were behaving as expected or if the design needed a little bit of tweaking. Since completion of construction in 2017, the instrument data has been downloaded twice per year. However, since the instruments are connected to the automatic data logger, this gives us daily readings for each instrument. So I'm now going to show you the instrument data that was collected during and since construction, and going to look at how it compares to the expected performance of the wall during design. I'll start with slope movement as measured with the slope inclinometers and Shape Accel Array. I'm sure many of you are familiar with these instruments, but for those who are not, I'm just going to give a brief description of what they are and what they do. So on the left is a picture of the slope inclinometer system. A PVC casing is installed into the ground with its bottom lower than the slip surface. At the time of reading, the probe, which is the long metallic thing on the bottom, it's connected to the cable and it's lowered to the bottom of the hole, with the wheels following along grooves in the casing. During casing installation, the grooves would be aligned so that they point in the direction of the highest slope movement. Once the probe is at the bottom, it's pulled up in increments. Some SIs come in 0.5 meter lengths, and the one that we use on this project is 2-foot increments. In each increment, the probe measures the tilt of the casing. These measurements are sent to the handheld data logger unit and stored, and this process is repeated until the probe is at the top of the casing. Then it's lowered again 180 degrees to the first reading, and the process is repeated. Knowing the distance between measurements and the angle from vertical, the horizontal displacement is derived. The Shape Accel Array, which is shown on the right, or SAA, is a series of rigid sections of constant length that's permanently left in the hole. Each section can move laterally, but they can't twist. And they have gravity sensors that can measure tilt in the X and Y directions. The X, Y, and Z position of each segment is calculated so that you can see the overall shape of the array, similar to an SI plot. And you can also see the change in position compared to previous readings. This photo on the right shows an installation of the SAA where they're uncoiling the array from this square and feeding it into a PVC casing in the ground. The SI plot shown here is from test hole 13-2, which is highlighted in the picture on the left, prior to construction of the wall. From this plot, there's clear movement between 17 and 18 meters depth, near where the lacustrine clay interfaces with the clay till. The maximum incremental deflection at this spot plots at nearly 25 millimeters downslope. This plot shows the change in measured displacement over time in test hole 14-4 at the slip plane elevation, which is just west of the wall section 4. In this plot, the displacements are shown to increase steadily from January 15th to June 2017, which corresponds to the time of anchor installation and lockoffs, the June 2017. The deflection rate levels off between June and September 2017 as construction is completed. Then it starts to increase again, but at a much slower rate between September 2019 and September 2020. The significant slowing of deflection rate in an SI downslope of the pile wall suggests that the pile wall has reduced the driving force on the portion of the slide mass that is downslope of the wall. Some creep is still going to occur, shown by the gradual increase of deflection with time, but the wall is expected to protect the highway, which was the main concern for this project. This is the SI plot for the same SI as the last slide. In the cumulative plot on the left, you look closely, you can see the red arrows here. This shows a big step of displacement between September 2016 and June 2017 when construction was taking place. Then you see all of the lines sort of on top of each other here, showing that the movement ceased or at least slowed down significantly until between September 2019 and June 2020, when displacement started up again, but more gradually. Drink break. This plot is from the SAA installed in pile P74, showing cumulative and incremental displacements starting during construction, which is January 2017, the green on the left, and finishing with the latest reading on September 2020, which is shown the red on the right. My arrow got moved over there. The zero depth of the plot corresponds to the interface between the top of the pile and the bottom of the whaler. By the end of construction, the top of the pile had been pulled 12 millimeters towards the highway in response to lock-off of the whaler anchors, and the pile had deflected up to 4 millimeters in the downslope direction at 16 meters depth. Over the period after construction leading up to 2020, some redistribution of the loading had occurred, reducing the pile deflection to 7 millimeters towards the highway and increasing the deflection near the slip surface to 7 millimeters downslope. These deflections are well below the serviceability limit of 50 millimeters of pile head deflection. I should note that an SI is encased in soil, so it's going to have a different response to slope movements than the SAA, which is encased in concrete. However, this does show the pile deflections are within acceptable limits. So looking now at strain gauge data, in this photo you can see the upslope and downslope strain gauge at this particular elevation connected to the rebar cage, which will eventually go into the pile. There's a tensioned wire between the two ends of the strain gauges, and as loading is added to the gauge, the distance between the ends changes, changing the tension of the wire. The frequency of the wire is measured in hertz, which is converted to a B value, then converted to microstrains using the instrument's provided calibration data and equations. Strain gauges can provide a few data sets. Total strains show the actual microstrain at each instrument. Bending strains are the changes in strain between the current and original readings. And the bending moments can be calculated from the bending strain using the flexural stiffness of the concrete. So I selected specific dates to look at the strain gauge data so that I could see how certain events were affecting strains in the pile. April 10th, 2017 was immediately after the upper pile row of anchors were locked off and excavation to the middle pile had begun. May 25th was after the middle row of anchors were locked off and excavation to the lower row began. July 10th was after the lowest row of anchors were locked off, and August 29th was when backfilling to final grade was underway. The total strains shown here show the measured microstrains on the dates that I mentioned earlier during construction. As you can see, the anchor installations are only in the top 5 or 6 meters of the whole pile length. Looking at the back of the pile, the April 10th reading, the total microstrains at the anchor elevations is about 40 microstrains in compression. But in the May 25th reading, which is the gray one, the strains suddenly shoot up to nearly 100 microstrains in tension. As construction continues, the tension strain starts to equalize as the yellow and blue lines peak at lower magnitudes. This jump in tension on May 25th is possibly caused by locking off of the anchors, pulling the top of the pile back towards the highway. These plots show the total strains after construction. Unfortunately, one of the strain gauges near the anchor elevation stopped functioning during construction, so we're missing some of the information here. But looking at this plot, the total strains starting at the finish of construction in August 2017 to our last reading in September 2020, the tension at the anchor elevation is continuing to decrease at the back of the pile, just below the anchor elevations. The strains appear to be gradually increasing in compression. Moving on from total strains, the next few plots show the bending strain on selected dates. This one shows August 29th, 2017, which is the end of construction. In the upslope backside of the pile, there appears to be a peak in tensile strain before a rapid transition to compression around the anchor elevation right here. This is also shown in the SAA as a possible inflection point in the curve of the pile. Generally, the upper half of the pile is in tension on the downslope side and in compression in the lower half, with the upslope side mirroring that with compression near the top and tension at the bottom. This reflects the result of anchors pulling the top of the pile towards the highway. The transition where the two lines cross also corresponds with an inflection point in the SAA plot at about 473 meters elevation. These plots show the bending strain on September 1st, 2020 compared to the SAA reading of the same date. There is some missing data, as I said, because of the strain gauges malfunctioning. But this SAA plot shows multiple inflection points along the pile. You can see it's a lot more jagged than the previous reading, and higher magnitudes in compression for both the upslope and downslope strain gauges. Finally, for strains, I took a look at the bending moments calculated from the microstrains and compared them to the theoretical cracking moment of the pile. The equation on the left is how the bending moments were calculated, and the equation on the right is the calculation for the cracking moment using the measured concrete strength from cylinders taken from site during construction. You can see from these plots that the cracking moment is exceeded in the end of construction and 3 years post-construction plots. Although cracking has likely occurred near the anchor elevation, there's no evidence of a significant hinge in the pile, so I believe that the steel reinforcement has taken up the tensile strain in the piles and the wall continues to function as required. Moving on now to anchor loads and load cell readings. This photo shows the load cell installed on the upper pile anchor. The load cell is installed between the bearing plate and the anchor cap and contains 3 sensors that read the compressive load and temperature using a similar wire frequency method as the strain gauges. Having more than one sensor on the instrument allows for more accurate load readings, even with mildly eccentric loading. These load cells were installed on all 5 anchors on pile P76, and load readings were set to be taken once per day. Both ultimate limit states and serviceability limit states were used in the design of the anchor loads. The design loads are shown here for the 5 rows of anchors. The upper anchors were locked off above the design loads with the expectation that the top of the wall will deflect away from the highway while the soil in front is being excavated. Then this deflection will be pulled back with the anchor loads and eventually slacken over time. The lower anchors were locked off below the design loads under the expectation that as the construction is completed, these anchors will pick up more load over time. As you can see in the final column, which is the most recent reading, they did act as expected, and the upper anchor slackened and the lower anchors increased in load over time. This is a plot of the two Whaler anchors load, also plotted with the temperature, which is in the gray. So the green is the lower Whaler anchor and the blue is the upper Whaler anchor. The two Whaler anchors show a gradual decrease in load between the end of construction, which is September 2017, to the current reading of September 2020, with local fluctuations related to the air temperature. When the temperatures are below freezing, loads increase by up to 7 kilonewtons. Then during times of warmer temperatures, the loads continue to slowly decrease. So this is the plot of the lowest anchor load cell, again plotted with the gray, which is the temperature. And you can see the temperature readings here are a lot less jagged, and that's because this one is buried, so it's taking the soil temperature, not the air temperature. So you can see the lower pile anchor load is increasing over time from a lock-off load of about 105 kilonewtons to about 121 kilonewtons in September 2020. Similar to the Whaler anchors, there is a sharp spike in load when the surrounding soils are frozen. Then the loads continue to increase gradually during warmer weather. I think I talked too fast. So with all this information and plots aplenty, what did I find out? Based on the slope inclinometer and Shape Accel Array data, there does appear to be some creep movement downslope of the wall, which is expected and is not going to impact the highway. Total and bending strains from the strain gauges show some inflection points along the length of the pile, but the strains are not of a magnitude that would be of concern. Bending moments show that there is some minor cracking in the pile around the anchor elevation, but that cracking is not significant enough to affect functionality of the wall. And finally, the anchor loads show that the anchors are picking up loads as expected and well within design limits. The overall conclusion, the wall is performing as expected and will likely continue to perform its function of protecting the highway. Thank you so much for taking the time to attend this talk. I wish very much that I could see all of your faces in person, but I hope you enjoyed it, and I'm happy to answer any questions.
Thank you so much, Leanne, for your presentation. My name is Leanne. As Kevin mentioned earlier, I will be the moderator for the Q&A session.
Thank you, Leanne.
So are you ready for the questions?
I'm ready.
Okay, let me pull out some questions here. I have one from Colin Drager. The question is, you mentioned if the design needs tweaking relating to the expected displacement, if the anticipated rate of deflection is exceeded, what is the contingency plan for that?
In this particular wall, I didn't see cases where that was required, but I did work on a similar wall where there were some concerning readings in the instruments. And so before construction continued, there were talks about whether another row of anchors was required or whether the anchors need to have higher loads. So I think there are several ways that you can tweak the design depending on what the instruments are showing us. Thanks, Colin.
All right, thank you. The next one is from Charlie Harrison. What was the controlling factor for the embedment of the secant piles?
The 30 meters was just, I think it was, in addition to getting obviously below the slip surface, there also had to be enough length that the passive pressure in front of the wall is providing enough resistance to the active pressure behind the wall. So it did vary. The other sections, I believe, had shorter lengths because they had less slips, a shallower slip surface.
Great. So far, I have no more questions coming up, but let me ask you a question based on my understanding. You said at the moment you measured from during time, you can see the concrete cracking, but you say that is not the issue, and because of the reinforced steel play a role there. So how would you be able to, let's say, identify a critical moment, like when the reference steel wouldn't work?
When you compare the bending moment with the SAA, if the SAA also shows significant hinging, and you can really see an inflection point that shows that you can kind of see that it just doesn't make sense. The inflection point, it's hinging too much. I think that would be when I start to be concerned. So I think it's the comparison of both the bending moments and the SAA together that would help me determine that.
Okay, well, thank you. And we have another question from Dr. Rick Chatonic. He said back in the early days of the design of this wall, was finite element modeling ever used to confirm the design?
It was not, but actually, sorry, I'm actually hoping to expand a little bit more on this project for a conference paper, and I would like to play with comparing these designs with the finite element method, because no, they weren't used.
Okay.
Rick
Great.
unmuted. I'm nervous now.
No, I was just going to say it was a perfect answer.
Oh, good.
That was perfect. Yeah, no, exactly. I did, because I think I remember you saying that it hadn't been used, and you at some point getting a chance to play around with that would be it'd be interesting to see what happens.
Yeah, it would be, definitely. And because that's how moving forward, that's how the designs are being done now. So it'd be good to compare.
Exactly. Yeah. Good for you. Good.
All right. Thank you again for your presentation. I saw lots of compliments in the chat here.
Oh.
And well done. And,
thank you so much for coming, everybody.
Yeah, thank you everyone for engaging in our seminar this semester. And we also appreciate all the speakers for making their time for the presentations. So before ending, I wonder if Kevin have any announcements or final words.
No, nothing special today. It's just thanks to everyone for their presentations and their time and making this a success this year. So, and thanks, of course, Leanne, for that great presentation.
Great. So with that, then just good luck to everyone with your study for the final, and see you next time. Have a good day.
Have a good day.
Bye.